Let us look again at the rate region for the dedicated message capacity. So in this case, we have only two dedicated messages for decoder 1 and decoder 2. And then we showed that this region here is achievable. So I want to point out these two special points, if alpha is equal 1 and if alpha is equal 0. So look at this point, if alpha is equal 1, then then the second dedicated messages uses the full power of the second marginal channel. So somehow one doesn't care about the dedicated message for receiver 2 or for its channel. So we reach this point, we have here the full capacity somehow of this marginal channel, and here the capacity to the decoder 1 is reduced by the mutual information of U1 and U2. The same thing here, if alpha equals 0, it's the equivalent case, but now we do it the other way around. But we want to concentrate now on the case alpha is equal 1. So if you look at this formula, this might remind you on some theory or on some model we had before. So if you remember, we looked at the model with the state of a channel and where the state influences the channel. And this was the Gelfand Pinsker model. So if you look at this point there, at this point with alpha equal 1, then we have R1 is equal to the mutual information of U1 and Y1 minus the mutual information between U1 and U2. And this is really identical to the Gelfand Pinsker rate if we consider UU2M to be the interference known non-causally at the transmitter. That means the transmitter knows before the sequence here. But this means somehow we do exactly what we did in the picture before, what I explained to you. And we can design it like Gelfand Pinsker did. So I already give a hint to this when we spoke about Gelfand Pinsker. So we can do it like it's shown here. So the source puts out W1 and W2 and gives it to encoder 1 and to encoder 2. For the case with alpha equal 1, encoder 2 do not care and just send everything through the marginal channel, but it gives his sequence to encoder 1. So, and this sequence somehow influences the channel of encoder, the marginal channel of encoder 1. So he knows U2 to the N and the message W1. And that's exactly the case we have for Gelfand Pinsker. And so he do somehow Gelfand Pinsker coding here, and then he sends XN. And from this XN, both decoder can decode U1 and U2 to the N. So here it's written again. This suggests designing an encoder as shown in this figure. The overall encoder consists of two encoders, one for U2 to the N and one for U1 to the N, based on Gelfand Pinsker coding. The output x1 to the N is a function on U1 to the N and U2 to the N, as in Gelfand Pinsker problem. We remark that in general decoder 1 and 2 will be able to decode only messages W1 and W2 respectively. So here you see exactly one application of Gelfand Pinsker for the broadcast channel if we only have two dedicated messages. This is one way we can use this coding scheme for the broadcast channel.